So we had these two regions. We wanted to find the area. And the idea, I drew this vertical, that's supposed to be like a straight line. It's supposed to represent a rectangle. And we're going to do the same thing on this one. So we're imagining this element at a random x, so we can think of it as at a random x value. And then as it slides through the region, we're imagining it as a very narrow rectangle, right? And the thickness of it, the width of it's dx, and the height of it is the top function minus the bottom function. And then it's going to sweep out the whole area as it slides from left to right. So in order to get the limits of integration correct, we need to know the start point and the end point here, the x values of those two. So for both of these. And of course, in order to find where two curves intersect, we set them equal to each other and solve for x. So that's what we're going to do for this one. Let's put in a little bit of space right here. And let's set these two equal to each other. So we have negative x squared plus 4x. Set it equal to x squared minus 2x. Put everything on one side. This is a nonlinear equation. Two principles from algebra. If you have a linear equation, variables to one side, constants to the other. If you have a nonlinear equation, the best approach usually is everything to one side and factor for a nonlinear. So this is nonlinear. I'll move everything to the right just because. Obviously, it doesn't matter which side you move it to. I don't want to have any negative leading coefficients, so that just makes it easier. And we can factor, divide out the 2 if we want. Let me divide out the 2 and just make a comment there. Obviously, there is a common factor of x on the right. We do not ever want to divide by a variable, though, because a variable can be any real number. It could be equal to 0. So you'd be dividing by 0. So that's why we put everything to one side and factor. We don't divide by x. We never divide by a variable in most cases. There are some weird situations. So if we factor that, we now use the zero factor rule. X is 0 or 3. So this tells us then that x is 0 or 3. That will give us our limits of integration, 0 to 3. So a little bit of algebra review. Hopefully nothing too mysterious. Although if there is some of this algebra trig that you're not 100% sure on as I'm doing it, just ask, and I can give you, a little bit of advice. Same idea over here. We want to figure out where these two intersection points are so that we can see where this vertical rectangle is sweeping through. We want to figure out the left and the right endpoint. Certainly looks like x equals 0 is the first one. But of course, we need to do the math. So to do the math, here we're going to set the two curves equal to each other. This upper curve is y equals 0, right? That's the equation for the x-axis is y equals 0. So we're going to set those equal to each other. So we're going to have cosine of x minus 2. And this is nice because it's already factored for us, right? That's already factored. And we have everything to one side. Right side is 0. Perfect for a nonlinear equation. So this tells us two things. This tells us that cosine of x is equal to 2, or sine of x is equal to 0. So 0 product rule. And where are the x values, or what x values cause cosine to be equal to 2? Yeah, not a lot of x's that have a cosine value of 2. We know that cosine and sine are both restricted to the interval -1 to 1. So no solution. This is going to contribute nothing right here. So we will get no solutions from there. And now, sine of x equal to 0. When we have a basic trig equation, I'll call them basic trig equations when we have a trig function equal to a constant. So when we have a trig function equal to a constant, you want to go to the unit circle. So the unit circle is where you almost always want to go if you have a basic trig equation. It's very rare that you're not going to go to the unit circle. Oh, and I just realized I could draw perfect lines. They have this new feature in here. I don't like that, but if I hold it, it will be a perfectly straight line. Okay. So the unit circle here, sine equal to 0, remember that it's alphabetical. Cosine sine x, y. Right? X first, y second. Cosine c comes before s. Cosine sine. Cosine comes first, so cosine is the x-coordinate. Sine is the y-coordinate. So sine is the y-coordinate equal to 0. So those are the two places on the unit circle. So that tells us that our angle is x equals 0, and then pi, and then 2 pi. And if we wanted to list all of them, we would say that this is equal to pi k. That would give us all solutions to that trig equation. The k is an integer. Positive or negative, doesn't matter. So that would be all solutions to that trig equation. Now we have to figure out, okay, well, which ones make the most sense? We look up here, it's like, okay, 0, and then the next solution would be pi. So we are going to choose 0 and pi as the two that we are going to use as limits of integration. 0 to pi. Make sense? Any drama there in your head?
Not about math.
Not about math. Not about math. That's good. If there's no drama about anything else, you're a bot. Okay, so now we have to integrate these two things. Let's do the one on the left first. The one on the left is very straightforward. We can combine some like terms and then integrate. Maybe we should write out those combined terms first. So we're going to have negative 2x squared plus 6x dx. Power rule, anytime we have polynomials, we just use the power rule. So we'll get negative 2/3 x cubed plus 3x squared from 0 to 3. And this will give us negative 18 plus 27, so I think we get a 9. Okay, any questions on that? Power rule, substitute, take the difference. Now we pop over here. All right. So let's just be very, very slow and methodical about this. So I'm going to separate this into two integrals. So we have negative cosine times sine. And then we know that the integral, the definite integral, can distribute across. And so I'm going to distribute it across and factor out this negative 2. This will also go 0 to pi sine of x. Okay, the second integral is immediate because we know an antiderivative for sine. An antiderivative for sine is negative cosine. So that one we can do immediately. This one we cannot do immediately. We have to use that technique that you learned at the end of Calc 1, U sub. And we have two choices. So when we look at this, we have a product. We have negative cosine times sine. We could let u equal cosine. We could let u equal sine. It's not going to matter. Both are going to work out just fine. Anyone have a preference? Let's let u be negative cosine. That is totally fine. So there's actually a few choices. You could do u equals sine, u equals cosine, u equals negative sine, u equals negative cosine. You have 4 choices. So if we did do this choice, this is actually a really good choice because now we take the derivative of both sides. The derivative of cosine is negative sine, and then we multiply by negative 1. That becomes positive sine. And that's going to allow us to rewrite this really beautifully, very nicely. So this will be u du. All right, that whole integral is going to simplify to u du. We said that negative cosine is the u, and its derivative is right there, the sine x dx. Now, limits of integration, 2 choices. We could convert to u's, or we could integrate with respect to u and then go back to x and then use the x limits. does not matter. Here it's easy enough to probably convert. So this is x equals 0. When x equals 0, cosine of 0 is 1, so the u limit is -1. When x is equal to pi, we put in a pi here. Cosine of pi, -1, multiplied by a negative, so that makes +1. Is that okay with everyone? And then over here, we're just going to do our integration. Integration of sine x, antiderivative is negative cosine x. That negative can jump out to the front and make that a +2 cosine of x. And then our limits of integration are 0 to pi. And then this integral, we're going to make that a u squared over 2. From -1 to 1. And we can plug these in here. Cosine of pi is -1 times 2, so that's going to be a -2 minus cosine of 0 is 1. 1 times 2 is 2, so we're going to end up with that. Which seems a little suspicious. I feel like something is not right. We'll find out in a second. So then this is going to be 1/2 minus what happens when we plug in the -1. So that's 1/2 minus 1/2, which is 0. And that's a -4 there. How this integral? So we get -4. Something is wrong there, right? So we have a sign error somewhere. You see it?
I think it was like the start, you didn't distribute the negative to the -2 sine x.
That could be. So we did 0 minus, so this is sine x cosine x. Okay, and that's positive, so the minus makes that negative. This is -2 sine x, and so that minus here that's supposed to get distributed did not get distributed. I assumed I did it right on Tuesday. Terrible idea. Okay, so that's a plus, which makes this a plus,
Makes the first two.
which makes, say that again? Does that change something over here?
No.
Yep, that's all good. And then when we integrate this, that's going to make that a negative right in here. So that is a negative, which is going to make this a negative. And then that is a positive, and that is a positive. That will be our area. Whew. Yeah.
I was just gonna say, you had two different limits of integration, one in U's, one in X's.
Yep.
As long as you keep everything valid and separate, it's okay.
Yeah, as long as we have that sort of invisible line between them and
Yeah.
we're treating this side with U's and this side with X's, we've sort of got that invisible line there so that
Okay.
the X's and the U's can act. Because again, the variable of integration is a dummy variable, so it's going to vanish in the end. Both of these integrals are representing constants. So whatever the letter of integration is, as long as we just keep it in that integral, we'll be fine. Question?
I was just confused when we did the u side.
Yep.
When we had the du equals negative sin x d of x, when we multiplied it by -1, where did that go?
So when we let u, so right in here, when we take this derivative, the derivative of cosine is negative sine, and then when that gets multiplied by this -1 in front, it becomes positive sine.
Oh,
You see it?
Alright.
And you could have chosen a different u. You could have chose u equals just cosine or just sine also, but if we do use this negative cosine as our u, we just have to remember that it's -1 times the derivative of cosine. And the derivative of cosine is negative sine, and then we multiply by the -1.
Okay, I see.
You see it?
Thank you.
The very beginning, where did that 0 come from? I'm just trying to remember from back.
And the 0 is this 0?
Yeah,
So when we look at our rectangle here, the height of the rectangle is the upper function minus the lower
oh, that's the
function.
0, okay, yeah,
The upper function is
Is
y
zero.
equals 0.
yeah,
So we're
okay.
thinking about the height of this rectangle, so we're going to do that function minus this function.
Yep, okay.
Makes
Perfect.
sense? Yep.
Where'd you get u squared over 2?
So
The derivative.
power rule says that you add 1 to the exponent and divide by the new exponent. So if we're integrating any polynomial, add and divide.
Gotcha.
So the power on that is 1, we add 1, we get a 2, divide by the new exponent. Yep.
One more question. So because that's just butting up against the x-axis, could you just integrate it and then you just get the negative?
Yes.
Okay.
So we could, like right here, we absolutely could just integrate this function, and if we just integrated that function, because it's below the x-axis, we'll get a negative, and we know because it is, tangent to the x-axis like that, we could just multiply by -1.
Okay.
Absolutely. Yep.
Which is basically what we did by doing 0 minus the function.
Exactly.
That's just multiplying by.
That's like multiplying by -1. Exactly.
Got it.
That is multiplying by -1. 100%. All right, so let's try a couple more. So this says find the area between these curves on a given interval. So let's take a look. Let's see. So we are looking at sine and cosine on an interval. We know that sine from 0 to 2 pi is going to look like that. We know that cosine is going to start up and then come down and then go up and then finish like that. More or less like that. Now, it would be really convenient if these two intersection points lined up with these two x values.
Guessing not.
Well, let's see if they do. So let's, again, if we want to know where sine and cosine are equal to each other, let's take a look at the unit circle. So unit circle, we are going to look at a lot. Unit circle, we want to have that down pat. Where are sine and cosine equal on the unit circle? So our perspective is different. Now on the unit circle, we're saying for sine and cosine to be equal, x and y have to be equal. The coordinates have to match. And so when we look at the unit circle, it's right here that the x value and the y value match, right, at pi over 4. X and y are both root 2 over 2. So actually, they've done us a favor, and that is pi over 4, because sine and cosine are equal there. And then they are also equal down in quadrant 3. If we come down to quadrant 3, at that point, both sine and cosine are negative root 2 over 2, so they match again, and that is at 5 pi over 4. So if we subdivide the unit circle into what I'll refer to as an 8-sector circle, 2 pi divided by 8 is pi over 4. Each sector is pi over 4, so there's 1, 2, 3, 4, that's at 5 pi over 4. So we just count by pi over 4s. So they did us good. We cannot always count on that. So there is our region that we're trying to find the area of. So we're going to draw our vertical element, our vertical rectangle, whatever you want to think of it as. I'm going to think of that as a vertical rectangle or vertical element at a random x. So I'll just label it as an x. That's just a random x. It's going to slide between pi over 4 and 5 pi over 4. So then our area is found by integrating from pi over 4 to 5 pi over 4. I really have to not, I'm not quite sure exactly why it wants to jump.
Is it your wrist too close to the board or something?
I don't think it's, I think it's more that I'm not like touching firmly. I think that it's just very sensitive. So what is the upper curve here?
Upper curve would be sine.
Sine. So we're going to do sine minus cosine. I think it's more that if it's at a slight angle. Like if it's perpendicular to the board, it really takes it. But if it's at a slight angle, it sort of, it interprets this as a fingertip because it interprets it bigger. Yeah. So does everybody agree with that? So this, we're thinking of it as a rectangle. The width of the rectangle is dx, this direction. The height of the rectangle is upper minus lower. Anytime we want a vertical distance, we're going to do the upper y minus the lower y. Whereas if we wanted a horizontal distance, we would do the right x minus the left x. So we're going to do upper minus lower. So that's going to give it to us. Now, both of those, we can integrate both of those functions easily. Antiderivative for sine is negative cosine. Antiderivative for cosine is sine. And that's pi over 4 to 5 pi over 4. There we go. Very close. Now we just have to do some evaluation. And we've already got the unit circle drawn up there, which is convenient. We need to know our unit circle values really well. And we know that at this point up here, it is root 2 over 2, comma root 2 over 2. And down here, it's minus root 2 over 2, comma minus root 2 over 2. So here, cosine of 5 pi over 4, that's the first coordinate right there, but then we multiply by negative 1, so this becomes root 2 over 2. Minus, now we're plugging in 5 pi over 4 there. There is sine of 5 pi over 4. Oh, it's negative, and that's a negative, so that makes this positive. And now we're going to subtract off the antiderivative, this whole quantity, evaluated at the lower end point. Let me put parentheses there just to keep it clean. So there's upper anti at that, now lower anti at that. So pi over 4, cosine of pi over 4 is root 2 over 2. Oh, but there's a minus, so there's a minus root 2 over 2. And then a minus right there, and then root 2 over 2 again. So we're going to have that. So when all is said and done, we have root 2 over 2 added to itself 4 times. So 4 times root 2 over 2. 2's cancel, we get 2 root 2. So that will be our area between the two trig functions. One thing I would like to mention conceptually is that if we look at an integral, there's 2 ways to sort of grasp what's happening. You can think of this in 2 ways. You can think of it conceptually as the integral and the dx being one symbol, and you're putting a function into that symbol, and then you're integrating. The integral symbol and the dx integrate that function. This function right here is height. Right? That's measuring the height here. And our result is area. So in our minds, we could say, if you integrate height, you get area. Or more generally, you could say if you integrate distance, right? Height is a distance. If you integrate distance, you get area. Or you can think of it more like physics people tend to think of it, and think of this as height and this as width. So you're thinking of the integral symbol as a sum, and it's adding up a bunch of little areas to get the total area. So it doesn't matter which way you think about it. Both of those are valid. You can think of this acting like a summation of all these little areas, all these little rectangles. Or more conceptually, integrate distance to get area. Now let me point out something that you may or may not have ever come across before. Somebody tell me the area of a circle. Pi r squared. What is the circumference of a circle? How did we go from there to there?
An interval.
This direction derivative, but the other direction integral. So circumference is a distance. If you integrate that distance, you get the area inside, which is the area of the circle. So that's how those 2 formulas are related. So if you integrate circumference, you're getting the area. Similarly, does anyone know volume of a sphere or the surface area of a sphere? If any, probably volume, if anything.
4/3.
4/3 pi r cubed?
Yeah.
4/3 pi r cubed.
And then 4 pi r.
So, and the surface area. So if we differentiated area, we got circumference. If we differentiate volume, we're going to get surface area. So the surface area is going to be 4 pi r squared. So if we integrate this way, we're going to take the surface area and integrate to get the volume inside of it. And vice versa, if we differentiate the volume inside, we're going to get the surface area that bounds that volume. So, question?
What happens if we take a 40 hypersphere?
Stop!
And
Stop! Yeah, we won't be talking. When you get to linear algebra, you can talk about things like that. So linear algebra is going to take, so what we notice is that everything in 2 dimensions extends to 3 dimensions, and you can do the same thing in 4 dimensions, and linear algebra studies that idea of letting your dimension move to n dimensions. And you can talk about the volume of a 4-dimensional sphere, which they call a hypersphere or whatever. But yeah, the same types of rules are going to apply. But we won't talk about it in here. We won't talk about that. But it's very interesting to think about. Okay, so let's go ahead and deal with this. Now we are going to see a ton of these fractional exponents. Fractional meaning less than 1. And 5/2 is a fraction, but it's not less than 1. Usually when we feel something is fractional, we think it's less than a whole unit, less than 1. And it's really important just to sort of get it in your mind that any of these fractional exponents, if you were usually interested in quadrant 1, they're going to be these bird wing looking things. So if we just look in quadrant 1, the numerator is going to affect whether the left-hand side goes up or the left-hand side goes down. But in general, we usually are looking to the right of 0, to the right of the y-axis. They're all going to have these shapes, like the square root function, the cubed root function, the 4th root function, the 5th root function. But in general, as long as that exponent is fractional, it's just going to be this bird wing looking thing all the time. So don't get hung up on plugging in numbers and things. As long as that exponent is less than 1, and we really only care about what's happening to the right, it's going to look like that every single time. That's all you have to draw every single time is that little bird wing. You know, and if you want to get technical, you can look and say, oh yeah, well the left side's going to be vertical here because we have an even exponent. Down here it's going to be negative because we have an odd exponent. This is not going to have one because the 4th root of a negative is undefined. Like you can get into those details. We don't care about those details in here though, because we're going to be looking 99% of the time 0 to infinity. So we just want to be able to be quick and efficient. Oh, we see a fractional exponent, it's going to look like this. You know, look almost like a log function that's shifted. It's not a log function. A log function goes through 1. Okay, so we see in this problem, we see one of these fractional exponents. So we're thinking bird wing, and we don't care what's happening to the left. The important thing is that it goes through the origin, and it's going to be some sort of arc. That's all we care about. We don't need to get precise. And then y = 4 is a vertical line. So we'll just think of that as the vertical line at 4. So there's our region, and they say first quadrant. They didn't give us a lower boundary, but then they do indicate first quadrant, so we do know that we are just going to be right there. So that's going to be the region that we're trying to find the area of. So we'll draw our vertical element, aka rectangle, very narrow rectangle. And we want to know, okay, what's the area of this region here? Well, the way we find area is to integrate a height function. The height function is this function x to the 2/3, that's the height.
0 to 4.
And then we're going to go 0 to 4. So we know our two intercepts are 0 and 4, so those will be our limits of integration. This is not a polynomial, it's a rational function, but we still use the power rule.
Isn't y = 4 horizontal? X is 4 is the vertical at 4.
Oh, I'm finding the wrong area. Thank you. Y = 4 is a horizontal or vertical.
I was gonna say.
Great.
Yeah.
Great, yeah. So when we are graphing, so when we say y is equal to 4, we want all the points that have a y value of 4. And because x is not in that equation, that means x is unrestricted. Now when you see an equation and a letter is missing, that means it's unrestricted. It can be anything. So when this equation is sitting here, that's how we know it's supposed to be horizontal. We want all the ordered pairs that have a y value of 4 in any x, because x is not in the equation, x is unrestricted. So great catch. So that changes things. That changes things. That will change things. So let's see where our region is then. So y equals 4 is going to be a horizontal line, not a vertical line. And that means that our trapped region, again, they said it was in quadrant 1, so our trapped region is there. That is our trapped region, and we'll call that a random x. Yeah. That will be a different area, right? That will be a different area. That will be a different area. So the question, though, is what is the height of our rectangle now? So the height of our rectangle, that's a vertical height, it's a vertical distance. Anytime we're measuring vertical distance, it's the upper y coordinate minus the lower y coordinate. The upper y coordinate is y equals 4. The lower y coordinate is y equals x to the 2/3. So we're going to have 4 minus x to the 2/3. So we'll have that.
And it's not from 0 to 4, right? It's from 0 to.
And now our limits of integration, yeah, we still have some things to change here. That is no longer, oh, it's still a dx, so that we don't have to worry about. But the x's are going to go from 0 to this point right here. So we need to figure out what the x value of that is. We know the x value here is 0, so we can slot that in. Now we want x to the 2/3. We're going to set that equal to 4. And then figure out what the x is. Now, this is a nonlinear equation. 90% of the time with a nonlinear, you pull everything to one side and factor. The one time you don't need to do that for a nonlinear equation is when you have a power of x equal to a constant. That's the one time you don't with a nonlinear equation. Because if you can isolate that power of x, set the other side to a constant. So when you have just an isolated power of x, you treat it more like a linear equation. And now we raise both sides to the appropriate power to undo that exponent on the left. So we'll raise both sides to the 3/2 power. So that will give us x. And we'll be doing a lot of this algebra type stuff. When you have a fractional exponent, you usually want to activate the denominator first. The denominator is the root part of it. The numerator is the power part of it. So when we look at 4 to the 3/2, we want to trigger this denominator first. So that's going to be the square root of 4, which is 2, and then 2 cubed, which is 8. So that'll be our process. You could do the numerator first. You could power it up and say 4 cubed, 64, and then take the square root of 64. But usually it's easier to do the root first because that shrinks the base, and then raise it to whatever the numerator power is. So usually it's better to do the denominator first. Most of the time. Okay, so then we do our power rule thing. And like I was saying, that's a rational exponent. It's not a polynomial, it's a rational function. But we integrate the same way we do for a polynomial. We just add 1 and divide. So we're going to end up with x to the 5/3, adding 1. And if you divide by 5/3, you multiply by the reciprocal. So we'll get that. Then we can go ahead and do our fundamental theorem of calculus. We'll plug in our upper limit, plug in our lower limit, and take the difference. So plugging in the upper limit, that'll give us a 32 minus. Once again, we have a number raised to a fractional exponent. Denominator first. Cubed root of 8 is 2, and then 2 to the 5th is 32. So we're going to have minus 3/5 times 32. Everyone agree with that? Cubed root of 8 is 2. 2 to the 4th is 16, so 2 to the 5th is 32. And let me point out something here. There's a lot of kind of quick ways you can do some of this evaluation. It's very tempting just to make this 96 over 5, get a common denominator of 5. But there's a faster way. There is a 32 that is common to both those terms. So if you factor that 32 to the front, you are left with 1 minus 3/5. That we can do in our head. We don't have to worry about dealing with the 96 over 5 thing. So this will end up being 32 times 2/5. And that's going to give us 64/5. Make sense? Why horizontal? Why horizontal? X vertical.
And then
Make sense? Now, with this region here, you actually could integrate it with respect to y instead of with respect to x. This region is both vertically simple and horizontally simple. And what I mean by that is this. When you are drawing your vertical element here, you can draw it anywhere you want, right? It's just a representative element. And as long as wherever you draw it, you have the same upper curve and the same lower curve, that makes it vertically simple. Your vertical element can go anywhere. So you can do a height thing as upper curve minus lower curve. This is also horizontally simple, right? You could draw a horizontal element, and the right curve, no matter where you draw that horizontal element, is always the same, and the left curve is always the same. So this one you could integrate with respect to x or y. Now, if you integrate it with respect to y, you would need to rewrite these functions so that they were functions of y. They were written in a way that x was isolated. So right here, we have these written as functions of x. Right? That's a function of x. It's measuring this direction. When you write it as a function of y, then it's going to measure this direction. So we could do that here and get the same area, and that's what this next slide's all about. So these regions here are horizontally simple, because when you draw your representative horizontal element, they have the same left curve no matter where you draw it. If you drew it there or you drew it there, the same left curve, same right curve. So it's horizontally simple. That is not vertically simple. If we drew a vertical element right here, the upper curve and the lower curve are whatever they are, and then you draw one over here, it's different. Right? It is not vertically simple because you do not have a consistent upper and a consistent lower curve. So this one we absolutely have to integrate it with respect to y. So we're thinking about, now when we think about the width of the rectangle, we're thinking of the width as being vertical, and we're thinking of it as being dy. And the height of the rectangle is like a sleeping rectangle. The height is this direction. The height is horizontal. So same for all of these regions here. All of these are horizontally simple, not vertically simple. None of those are vertically simple. So we're going to have to integrate with respect to y instead of x. And it's the same thing. This is still the height of the rectangle, and this is still the width. So we're still adding up a bunch of rectangles. It's just that they're stacked this way, like a deck of cards. So that height, horizontal now, the height is horizontal. When you're measuring a horizontal distance, it's right minus left. Right? If you think about the number line, if you go from x equals 2 to x equals 10, that distance is the right x, 10, minus the left x, 2, gives you 8. Right? If you did it the other way, you'd get a negative number. So we want to do right minus left. So when we look at this region here, we want to find this area. You could, if you wanted to be really, if you wanted some extra work, you could break it into two regions, and you could do it with a dx. It's going to be much easier to do with a dy. So let's draw a horizontal representative element right there. That's going to be at a random y. Okay. Now, if we are 100% sure that this region is symmetric about the x-axis, we could find this upper area and then double it. Right? We could find this area and then double it. We know for sure that x equals absolute y. That is symmetric about the x-axis. How do we test whether this function is symmetric about the x-axis? So you could do that. So there's a trick in algebra that you learned. If you wanted to find out whether something was symmetric about the y-axis, you plug in x and minus x and see if the y's are the same. Right? If you replace x with negative x and you get the exact same function, then you're symmetric about the y-axis. If you want to do symmetry about the x-axis, you plug in y and you plug in negative y, and you should have the exact same x. So plug in y and negative y. Okay, well, there's y. So if we replace that with negative y, and it doesn't change the function, then it's symmetric about the x-axis. So if we do that over here, if we say, so we have x equals 2 minus y squared, if we replace that y with negative y, and then simplify, these two are now equal, so therefore this function is symmetric about the x-axis. Because whether you go up to y or down to negative y, you end up with the same x. So that means it's symmetric about the x-axis. Okay, so we can, so therefore symmetry about the x-axis. So that allows us to just integrate the top half and double it. Now let me ask you another question. Absolute value of y is a piecewise defined function. And we can see the graph of each piece. This is one piece of that graph. And then down here, this is a second piece of that graph. Each of those pieces can be written as a function. What is the equation of this piece up here? X equals what?
X equals y.
X equals y. And what is the equation of this piece?
X equals negative y.
Correct. Right. So if we wanted to, we could also approach this by finding this upper area with that function as the left function, the lower area with that function as the left function. So lots of different ways that we could get at this. Let's go with our original concept of using symmetry here. So our total area will be double the integral from 0 to something. We'll get that in there in a minute. So remember, the height of our rectangle is what goes inside our integrand. And the height of the rectangle, it's a horizontal distance. Anytime we do a horizontal distance, it's right x minus left x. So the right x, right there, 2 minus y squared. So 2 minus y squared is the right x. 2 minus y squared. Now we're going to subtract off the left x. The left x is x equals y. So we're going to subtract that off, be y. And now we need to know this point of intersection right there. So let's figure that out. Let's come up here. So we're going to set these two functions to equal to each other. So we're going to have y equals 2 minus y squared. That is a classic nonlinear equation. Everything to one side and factor. So we end up with y squared plus y minus 2 equals 0. Factor that. So we're going to end up with y minus 2 times y plus 1 equals 0. Nope, y plus 2 and y minus 1. I have them backwards, don't I? So these, we need to preserve a positive. So the positive should be next to the larger constant here. So that should do it. 2y minus y, so that'll work. So we get y equals 1 or negative 2. Which one is it? 1. What does the negative 2 represent?
Where it would cross if x equals y kept going into the third quadrant.
100%. So if this curve, this line, continued on this way, if we let it keep on trucking, well, eventually this parabola and that line are going to meet a second time, and those are going to meet when y is equal to negative 2. It is not the y value for that intersection point. Right? That intersection point is going to be negative 1. Yeah. So now we're ready to roll with our integration here. So we'll leave the 2 out in front. Integrate a constant, we get 2y. Integrate y squared, we'll get minus y cubed over 3. Integrate y to get y squared over 2. And that will go 0 to 1. And that is a 2 right there. If we plug in the 1, we end up with 2 times 2 minus a third minus a half whatever that adds up to. Seven over 3? I don't know. Somebody double check. Sometimes it's good to have a scientific calculator.
7/3.
7/3, right?
Yeah.
Oh, good. Even blind squirrels. Okay, here's another one. Why don't you all try this one? So we want to find the area of this region. It's going to be horizontally simple, so we use a horizontal rectangle or element, integration element. At least get it set up. Yeah, it changed. Sorry.
Did you make it bigger?
At 30.
What's that?
Did you make it bigger?
Yep.
Thank you.
Because it has to be simple across the entire range.
Yeah. Otherwise, you have to do weird things where you like cut it in half and then
Subdivide.
That makes it a mess. Because if you like think about setting up like, well, also it's not a function in the x direction.
The red one.
Shares y values basically. It's not a function of x. That makes sense.
Let me know if you're running into any snags. This one just looks more tedious than complicated. We've already isolated x for us, so we already have our functions measuring horizontal distances, so that's convenient.
Is the right equation in the top one? The right equation is the bottom.
So this one is the right equation right here. That one is right. This one is left.
If you did it wrong, you just end up with a negative area. What's it?
And as soon as you end up with the negative area, that's the first thing I would check is, oh, did we do the subtraction backwards? And if you didn't do the subtraction backwards,
You did something.
then you got to dig deeper. Dig deeper. I'll find the intersection points up here as you guys are slogging away.
That's just kind of
So that's the integrand you should have ended up with. Negative 3y squared minus 3y plus 18, that is the right function minus the left function with like terms collected. And negative 3 and positive 2 are the intersection y values. Any issues up to that point? So we do right minus left, and then we integrate with the power rule. And then we're going to plug in our upper limit. And then subtract off the lower limit evaluation. And then whatever all that equals to, I'll add it up during the break, but whatever that adds up to. Any piece of that you're not 100% sure on? So if it's horizontally simple, we integrate lower to upper. So we're integrating this direction instead of integrating horizontally. Let's try another one. So here, this function, this region is both horizontally simple and vertically simple. So let's do it both ways and just confirm that we will get the same answer. So the first direction I'm going to integrate is with a vertical integration element because the functions are presented as y values. Each of these are presented as y values, so they're presented in a way that they're measuring vertical distance already. So let's go ahead and do that one first. So if we look at it this way, let's go ahead and notice that this intersection point, do you see that that intersection point is going to be 1, 1? You could set them equal to each other and solve, you'll get 1. If you plug in x equals 1, both those y values are 1. So our integral, the red direction, let's do this with a dx. This is going to integrate from 0 to 1. The height is the upper function, which is square root x, minus the lower function, which is x cubed, and then a dx. So that is the area using a vertical integration element. So this will end up being x to the 3/2 times 2/3 minus x to the 4th over 4, 0 to 1.
Oh, maybe it's, yeah.
So this will be 2/3 minus a 4th, which is 8 minus 3, 5 over 12. So that would be using a vertical element. Now let's go with the horizontal element. So let's suppose instead we wanted to go with a horizontal element at a random y. We'll get the same answer. Our area, we still are integrating 0 to 1, but the 0 to 1 is on the y-axis, not the 0 to 1 on the x-axis. And then we're going to do right curve minus left curve. The height of our rectangle, our horizontal rectangle, the height is right minus left. So the right x value. Okay, this function is written as a y value, not an x value. So I need to change it. I'm going to write it as an x value by taking the third root of both sides. So now the right function is written as an x value, y to the third. Similarly, the left function needs to be written as an x value, so that'll be x equals y squared. So now they're both written as x values. We're going to do the right x value minus the left x value, and then a dy. So we add 1 to the exponent, divide by the new exponent, so we're going to have y to the 4/3 divided by 4/3, and then y cubed over 3, 0 to 1. We're going to get 3/4 minus a third, which is going to be 9 minus 4, which is 5 over 12. Same thing. As we would expect. That's why we like math. Any issues or questions? All right, let's do our last 6-2 question. Here's our last 6-2 question. So we want to find the area. Okay, so we have the sine function, y equals sine of x. And we know what that looks like. Y equals sine of x starts at the origin and ends up doing this on the interval 0 to 2 pi. So there's, and pi is in the middle, 2 pi is over here. So there's y equals sine x. Of course, it keeps going both directions. What is this equation? What is the graph of that? Parabola. It's a quadratic. X squared minus pi x. It's quadratic. It's going to open up because x squared has a positive 1 coefficient. Now, it's pretty easy to graph that because they've already factored it for us. And so we know that the zeros, if we set that equal to 0, we are going to get 0 and pi. So that tells us these are those are where the parabola crosses the x-axis. We know the vertex is right in the middle. We don't really care where the vertex actually is. All we care about is this relative shape so that we can keep upper and lower distinguished. So that's roughly what the parabola is going to look like. If we wanted to know exactly what that y value is, we would just plug in pi divided by 2 and figure it out. But we don't care. So there's our region, looks like an egg. We want that. That's going to be the height right there. This is at a random x. We're going to slide from 0 to pi. Not too bad. So our area will be the integral from 0 to pi. The height of our rectangle is the upper y value, which is sine of x, minus the lower y value. And the lower y value is that thing. Let's distribute that so that we can integrate it easily. So we're subtracting off this function. That function is x squared minus pi times x, and then a dx. So upper minus lower times the width of that red rectangle. The width is dx. We can distribute and integrate. Probably do that all at once. Integral of sine, negative cosine. Integral of negative x squared is negative x cubed divided by 3 plus integral of pi x. We add 1 to the exponent and get x squared divided by the new exponent. We get 2. This is going to go 0 to pi. Plug in pi first. Cosine of pi is negative 1. Negative 1 times negative 1 is positive 1. So that's going to be a 1 minus pi cubed divided by 3 plus pi cubed divided by 2. And then we subtract off antiderivative evaluated at 0. So minus, well, it's minus a minus.
Oh,
So
yeah,
it's
yeah.
plus. Cosine of 0 is 1. And plugging in 0 to those two gives 0. So our final answer is 2. If we combine these pi cubed terms, we're we're going to end up with, let's see, so if we multiply that one by 3, we're going to have 3 pi cubed there and minus 2 pi cubed, so we're going to get 1 pi cubed over 6. And that'll be the area. All right, let's go ahead and take a 10-minute break. If you have questions or we want to look at any problems, let's pull them up and we'll figure them out. Oh, and then I'll take a roll when we get back.
This is my area. 2 plus.
Let's go. So, third dimension. That's where we live, so let's hang out in the third dimension for a little while. So one concept that we just sort of talked about a little bit is that if you integrate height, or distance in general, you're going to get area. And now we want to step up one notch, and if you integrate area, you will get volume. So that's going to be sort of the underlying concept, that if we integrate an area function, we're going to get a volume. So that's what's going to go on here. Now, we're imagining this volume, and the idea is that we want to create slices, and a slice is going to be a cross-section is going to be 2 dimensions. So a cross-section is 2 dimensions, and then when we call it a slice, we're really thinking of adding a little bit of thickness to it, like the dx or the dy. So we're all of a sudden turning it from a 2-dimensional slice into a 2-dimensional cross-section into a 3-dimensional slice. But that slice is super thin, right? It's like thickness dx or dy. So here's our cross-section, and then that is a slice. So a slice is more like a slab. Adds a little bit of thickness to it. And the idea, of course, is the Riemann sum idea. If we find the area of our cross-section, multiply it by the thickness so that we now have the volume of a thin slice. If we add up all those slices, we get a good approximation for the volume of the object. And then we wave our hands, we take the limit of the Riemann sum, and the limit of the Riemann sum gives us a definite integral. So that's what you did in Calc. You did a lot of that in Calc 1, sort of convincing yourself that the limit of a Riemann sum is actually a definite integral. And so we will find, as we let n increase, that's the Riemann sum idea, we get a better and better approximation. And then when we take the limit and let n go to infinity, we will get the exact definite integral, which will be the volume, the exact volume. So that's our idea. So we need to find a cross-sectional area function in order to integrate it to get the volume of the solid object that we're referring to. So here is our first example. We've got this solid object down here, and we want to look at the cross-sectional area function and then integrate it. That's the basic idea. Integrate area to get volume. Okay, so here is the xy plane. So in the xy plane, we have this curve y equals root 3 minus x, so it's just a shifted square root and reflected. And we have the line x equals 2 right there. So we're looking just at this. This is the xy plane portion that we're looking at. This is the base of our solid object. So the solid object is coming straight out of the board. That makes sense? So that highlighted yellow is down here over on this picture. Down there, it's the base. It's the base of the solid object down there. So there's the base of our object. And then they tell us that the cross sections, they're perpendicular to the x-axis. So there's going to be a couple of ways to talk about our cross section. So here's our base. Our cross sections are always going to be perpendicular to the base, right? That's how we're creating them. So they're always perpendicular to the base. But then they could be perpendicular to the x-axis or perpendicular to the y-axis as well. So they're certainly perpendicular to the base. But then we have to decide, okay, well, what's the orientation of that cross-section? Is it perpendicular to x or parallel to x? Is it perpendicular to y or parallel to y? So they're telling us that it's going to be perpendicular to x. There's the x-axis there. So there's our base. We're going to stay perpendicular to x. Perpendicular to y would be like that, which would also be parallel to x. So you could describe the orientation of those cross sections in 4 different ways. Parallel x, parallel y, perpendicular x, perpendicular y. But they are always perpendicular to the base, right? Okay, so, and they tell us that they're squares. So let's zoom into the xy plane. Down here in the xy plane, there's our region. They say that we're perpendicular to the x-axis, so that's why I drew a vertical integration element there. So it's perpendicular to the x-axis. And the cross-section is a square, so this is going to come straight out of the board and form a square that has dimensions, whatever that red dimension is, on each side. And then the area of that square will be that dimension squared, that distance squared. Okay, so if we imagine taking that red element and we imagine pulling it out of the board, it's going to create this red rectangle that's coming straight out of the board. And the dimensions of our red rectangle, well, let's see. This is the x-axis down here. So the length of this side right here is whatever that function is. That function is measuring, right, the side length of our square. So this square has to have the same dimension on each side. That's an x. So the area of the red square is going to be root 3 minus x squared, which is 3 minus x. So that x value, we imagine it moving from 0 to 2. If we plug in a 0 there, that locates us right here. And look, the dimension of the square is going to be a 2 by 2. Oh, no, that's not 2. What is the height right here? If we plug in 0 there, what is this height? Square root 3. So that's square root 3. So the square when x is 0 is root 3 by root 3, so its area will be 3, which is what we would get when we plug in a 0 to the area function.
Or why is it square? The shape on the board's not a square, yellow shape's not a square.
That right there?
No, the yellow. And why, it's not a square.
No, the yellow is the base. The square is found from this red segment, and that square is coming straight out of the board. So this red segment creates this red square, which is this square right here. Oops. So that square right there is that red square over there. So the area of that red square is going to be base times height, which is root 3 times root 3, which is 3, which the area function will give us. If we plug in the other endpoint, let's come over here. So there's a 2. The height right here is what? What is that height?
1.
That height is going to be 1, correct. So if we come over here to x equals 2, this height right here is 1. Because if we plug x equals 2 in there, 3 minus 2 is 1, square root of 1 is 1. And if we plug that 2 in right there, we get a 1. So that square on the end is a 1 by 1 square, which will have area 1. So we can find it, sort of by thinking here that each side length of this square is 1 and 1. Or you can take the 1 and plug it in right there and get your area. Or the 2. Plug in the 2 right here and get your area. At x equals 2, we get a 1.
That's the one closest to us.
And that's the one closest to us. So the green square right here, that is generated from that. Yeah. Okay, now to find the volume, all we do is integrate the area. And that's going to be this. So our volume will be the integral of the area function with respect to x, and x is running from 0 to 2. That'll be the volume. So we integrate an area function to get volume. So this will be 3x minus x squared divided by 2 from 0 to 2. Plug in the 2, we're going to get 6 minus 4 over 2, so 6 minus 2. So our volume will be 4. Yeah, so when we look at the base of our solid, they have the x direction this way, so this yellow region is, rotated up here. So there's the green piece on the right side up there. If you rotate it, it will match.
Like, do you not really care about units at all? Like if
This is math.
yeah.
We don't care about units.
Okay.
So yeah, if the problem gives us units, we'll tag them on there. But many of these math problems, they don't put any units, so we don't need to put units. Even you could put 4 cubic units if you wanted, but yeah. But yeah, a lot of these math ones, they won't even ask about units. Hence the disaster on Mars. Okay, so let's take a look at another one. So here we've got our base region. So this is going to be the base right here. And we're going to do some things a little bit differently here. We're going to take this and we're going to rotate it around the x-axis and create that parabolic solid. Well, it's not parabolic. You know what I mean, though. It looks parabolic-ish. So it's going to look kind of like a paraboloid. It's going to look like a bullet. And when this region rotates about the x-axis, what shape are the cross sections going to be? They're all going to be discs, right? Every one is going to be a disc like that. Okay, so we can envision this coming down, like that, and then this is going to create a disc right there. So that's going to be the shape that we want to find the area of and then integrate that area to get the total volume. So the area of a disk, in general, that's pi r squared. Everyone agree? Area of a disk, pi r squared. Now the function that's being used here is root cosine x. That is acting like the radius of the disk. So root cosine x is measuring the distance from the x-axis up to this curve. Well, that's the radius of the disk. So when we find the area of a generic disk here, it's going to be pi times the function root cosine of x, quantity squared. So we're going to get pi cosine x. That is the area of the disk at x. So let's just check a couple of extreme points just to see if we're on track. So if we come all the way over here to the tip right there, what should be the cross-sectional area? 0. So let's check. Okay, the x value there is pi over 2. When we plug in pi over 2 for that x value, do we get 0? Yeah, cosine of pi over 2 is 0, so that's matching. It seems like everything's on track. Let's come to this edge right here. So if we come to this edge right here, the radius there is 1. The area of that corresponding disk should be pi 1 squared, which is pi. So when we plug in a 0 over here to our area function, we get cosine of 0 is 1, 1 times pi is pi. So that, if we check both endpoints and we get the right area, then we probably created our function properly. So now, the volume of this solid is just the integral of our area cross-sectional function from 0 over to pi halves. So that will give us the area of that, or the volume of that bullet head.
Can you explain that?
Yep.
You said the cross-sectional function?
So the cross-section, so here's our cross-section.
Okay.
So we want to come up with the area of our cross-section as a function of x. This is the area of our cross-section as a function of x. And if we integrate our cross-sectional area, that'll give us volume. So integrating area jumps us up to volume. Integrating distance jumps us up to area. Now you could also use that other concept I mentioned earlier. You could sort of say, okay, instead of integrating area to get volume, that's much more abstract, you could say, okay, well this is the cross section, and then when you multiply by the thickness, This is giving you the volume of a slice.
You can think of that as x times y times z.
Exactly. So you can think of this as a three-dimensional slice, and then the integral is just summing up all those little volumes to get the total volume. So you can think of it that way also.
And if you had units, dx would just be another unit.
dx would be a unit of length. So if we look here, this is going to be area, and dx is a distance. It's a small horizontal distance, so that's going to have the same units, you know, meters or whatever, units of length. So the units of the combined integrand with the differential, those should have the same units as what's on the left. Which is a lot of, that's how in physics you approach it that way all the time. You just make sure the units match, and then you're probably on track. Units are a good gauge. And then this is a pretty easy integral. The pi can factor right to the front. Constants factor through integrals and derivatives. And then the antiderivative for cosine is sine. So we're going to have pi sine of x on the interval from 0 to pi over 2. And we end up with pi over 2. Sine of pi over 2 is 1. Sine of 0 is 0. Say that again? Oh yeah, where'd the 2 come from? Thank you. Madness. Madness. When we plug pi over 2 in here, sine of pi over 2 is 1, and 1 times pi is pi. Yeah, thank you. And sine of 0 is 0, so the lower limit of integration doesn't give us any volume. All right. So let's take a look at this GeoGebra app.
Real quick question.
Yeah.
So does that mean that that is a hemisphere of a perfect sphere then, technically? In the areas, or am I missing?
Oh, I don't know. Let's think about that. Say that again.
Because the radius is pi. No, the radius is 1. Never mind.
Yeah, the radius of this piece is 1.
Yeah.
This dimension is pi over 2, so it's not quite a hemisphere, but yeah. So there is a really good app.
It's a hyperbola.
Have you all heard of CalcPlot 3D? CalcPlot 3D is the three-dimensional equivalent of Desmos. Desmos is now doing some 3D stuff, but CalcPlot 3D is a really great. I'm not going to use it a ton because it's more like a Calc 3 type thing, but they did add this awesome feature a number of years ago that. So here's CalcPlot 3D. So if you just go to Google and type CalcPlot 3D, just type that in. You'll get to this. This is the default screen in CalcPlot 3D. And it's going to be more useful in Calc 3 because you can do all your surface stuff, and if I click home, it will reset it. But in this drop-down menu, they've now added surface of revolution not too long ago. And you can visualize how the solid of revolution is happening. So you can, and I need to play with this a little bit more. I want to get that function gone. And then I want to turn on this 2D thing, which is up here. So now we're over there. There's our region, and we're going to rotate that, and it's going to show us what that solid object is going to look like. And then you can, do all this kind of cool stuff, and hit home if you want to reset it. There's some keyboard commands to rotate just on the X and Z axis, and I'm forgetting what they are off the top of my head. But it's a really great app as you go into Calc 3 to be aware of. So CalcPlot 3D. And he's got the guy, and you maybe have heard of this guy. If you ever have looked up calculus notes online, have you ever come across Paul's online notes? Have you seen those? If you search for calc notes, any sort of calc stuff, his name will come up. His name is Paul Seeberger, and I used to go to conferences with him like 25 years ago, and he got this NSF grant and created this CalcPlot 3D about 20 years ago. And then he added in the surface of revolution thing a few years back. But it's a super great app. And then there's another app called GeoGebra, which is what I built this thing in. And let's see, why can't I reload that? Let's see. There we go. Somehow I have like a thing there. Not sure what it is. So this just is an app that's going to kind of show us how a region is, how you can imagine your cross section moving through the region, and you can edit this. So right here I have these are the curves right here, and if I tilt this I can see, you know, the parabola x squared, and the green line is y equals 4. You know, and then that's the solid object, and the cross sections are squares, kind of like the one we just did. And if you slide this, you're going to see the square slide through the region. So the idea, again, is that we just have all these cross sections that are squares, and we're basically going to add them all up. And you can change the opacity on here, so you can kind of see that rectangle sliding through, that square sliding through. If you want, you can change these functions up here and, you know, put in whatever you want. And then you can rotate it and look and just sort of get a sense. Sometimes it's not obvious, you know, what the shape looks like when it says, oh, all the cross sections are squares. It's not always obvious that you get this nice, clean, solid object. Like sometimes you think, oh, maybe it's going to be poking out one way or another. So some of these apps like CalcPlot 3D and GeoGebra are really good for getting a better sense of what's happening. All right, so let's try this one. So here we have a semicircular base. And so when we say base, you're imagining the solid sitting on top of the base. The base is sort of down in the XY plane. And then we are indicating what kind of cross sections we're going to have on this shape to build the solid object. So this tells us, and I said semicircle, it's like a semicircle. It's maybe not exactly a semicircle because we have a trig function, but it's like a semicircle. So we have this base region, square root of cosine x right there, and the x-axis. And we have our interval minus pi over 2 to pi over 2. And the cross sections through the solid are perpendicular to the x-axis, and they are isosceles right triangles. Okay, so we've got our base. They tell us now we're going to put in all these triangles, but now we have to orient the triangles. They haven't told us what direction the triangles are. They're definitely perpendicular to the base, but we don't know. Are they parallel to x, parallel to y? So we look a little further, and the way they tell us, so they say the horizontal leg in the xy plane and a vertical leg above the x-axis. So horizontal leg in the xy plane and a vertical leg above the x-axis. So that means perpendicular to the x-axis. Yeah?
It also says whose cross sections through the solid perpendicular to the x-axis.
Perpendicular to, oh yeah,
Alright,
thank you, yeah. Yeah,
Does that mean like Z?
that's what the part I wanted to highlight first.
So I mean, when you're saying that, does that mean the length that goes into the y direction like this, same as this?
Yeah, that'll make it isosceles. So the distance in the y direction has to match the distance in the z direction, yes. So those two have to match for it to be an isosceles triangle. Okay, so
It's right, it is actually entirely in the z direction instead of being angled. If it wasn't
That's
an
right.
angle, it could be.
right, yeah, so it's not tilted in any way. That height is going to be purely in the z direction, perpendicular to the base. So it's not tilted in any way. So we have to find the area of an isosceles triangle. So the area of an isosceles triangle, so an isosceles triangle, if you, actually I should just do the shape, right? It'll do the whole thing for me if I, so if we take an isosceles triangle, let's call this the base and that the base because those have to be the same thing. And if we want to find the area of this, so the area is going to be 1/2 the base times the height. So we're going to get 1/2 base squared. Everyone okay with that? So half the base times the height, and the base and the height are both the same. All right, so what is acting as the base in this case? Yeah, that square root of cosine is acting like our base. So the area of our triangle is going to be 1/2 times root cosine squared. So this is going to be 1/2 cosine x. So that is the area of the isosceles triangle at x. Let's just double check. So if we come out here, they tell us that this is going to end at pi over 2 right there, and this is going to be minus pi over 2 back there. Those should give us areas of 0, because we've pinched down to a single point. So let's check. Plug in cosine of pi over 2. Cosine of pi over 2 is 0. Cosine of negative pi over 2 is also 0. So yeah, that matches. So now the volume, we could use symmetry here. Symmetry is a good thing usually because when you have a limit of integration that's 0, that's always helpful. So let's go ahead and use symmetry. We know that the solid to the, that side of the y-axis in the negative x direction and this side, those have to be the same. So the total volume is going to be 2 times the integral from 0 to pi over 2 of our area function. Right? Yeah, if you see it right, it can feel very easy. If you see it right. So we get sine of x from 0 to pi over 2. So there's our volume. A nice integer. No pi's, no irrational numbers. The volume of that thing is 1 cubic unit. That wedge. Seems pretty straightforward. It's got to get worse, right? It's got to get worse.
It's really straightforward because I picked nice equations that all cancel out.
Yeah, squaring the square root function. Okay, we can do that a lot.
Yeah, that's free.
Okay, so there are 2 ways to generate these solid objects. One way is by construction, where they tell us what the cross sections are. So they tell us that the cross sections are triangles or squares or semicircles or whatever. So we can build the solid with these cross sections. They call that the general cross section method. Now we're going to look at a more specific case that we're going to spend more time on, where we have specific cross sections that are created by rotation. And so we're going to see 3 different methods. We're going to see the disk method, the washer method, and the shell method. These are going to be 3 ways to create solid objects. So again, if we're going to do a rotation and the region is touching the axis of rotation, you're going to create cross sections that are disks. So right here, we're rotating around the x-axis, so we are touching the axis of rotation. So when that rotates around, we're going to create a cone. And there's a cone, I took that from CalcPlot 3D. So you can see a cross-sectional disk, and I kind of opened it up so you can see the cone and then what it looks like inside the cone with that one cross-sectional disk. So that's like so that red disk down there is from that vertical element. It's going to create that red disk. Okay, so this is the vertical element at x. Vertical elements you can always locate at x, horizontal you can always locate at y.
So basically, is it like, you have the like graph right here, and you're spinning it around out of the board and behind the board?
Correct. Yep, that's
Okay.
exactly right. So this triangle is going to spin forward out of the board and then go back into the board and create that cone in this case. So we need to know the area. So this vertical element is going to act like the radius of the disk. So as that rotates around, it's going to create a disk. So we're going to have a disk in here. And the area of a disk is always pi r squared. So the area of this disk is pi times the radius squared. And the function is acting like the radius. Right? This function is measuring the distance from the axis of rotation up to that tilted line. So that is our radius. So the radius gets substituted with this 2 minus 2x. And now we have the cross-sectional area at x. And once again, if we check our extremes, we should be able to confirm that that's probably the right area function. So if we look at x equals 0, the radius of the circle would be 2, so we should get an area of 4 pi. So if we plug in 0 here, yeah, we get 4 pi. If we go to the other extreme out here, we should get an area of 0, right there at the tip. So if we plug in a 1, 2 minus 2, we get 0. So you can always double check that your area function matches. And now we want the volume of this whole cone. The volume of that cone is going to be the integral from 0 to 1 pi multiplied by, we'll square that out. So this will be 4 times x squared minus 8 times x plus 4 if we write it in descending order. And we can factor out the 4, or we can just leave the 4 in and integrate, doesn't matter. It will all come out in the wash. So this will be 4x cubed over 3 minus 4x squared plus 4x. And that will go from 0 to 1. And plugging in 1, we will end up with pi multiplied by 4/3 minus 4 plus 4. And that's going to give us 4 pi over 3 cubic units. So that'll be the volume of that cone. Good? Does anyone know the volume of the geometric volume of a cone?
1/3 base area times height.
1/3 pi r squared a. Yeah, what you said. That's right. So the area of a cone is 1/3 pi r squared h. So if we look at this cone, we get 1/3 pi. R is this area over distance here, so that the radius is 2. So that's going to be a 4, and then the height is 1. So yeah, we get the same thing. Woohoo!
Always a good time.
Always good. Always good. Get the right answer. Feels so good to get the right answer. Okay, here's another one. So rotating around. So you all try this one. So we have e to the negative x, that's exponential decay. We have y equals 0, which is the x-axis. We have x equals 0, which is the y-axis. And then we have the natural log of 4 to create this region. And that region is going to be rotated around the x-axis, creating this kind of sideways tower thing. So see if you can find the volume of that solid of revolution. Let me know if you have any questions, if you're stuck on any of the things. Is there anyone I didn't get on roll? Did I get everyone? Let's see. Your first name is?
Villalobos.
And your first name?
Seth.
Oh, right at the top. How do you say your last name?
John Cho.
Chancho.
Yeah.
Is that how I would have said it?
That's not how anybody says it.
Right? I can imagine. Also sounds Italian?
Yeah.
Yeah.
Still working on it. For the,
Looking good.
integral,
Check there.
I to the negative 2 over 2, right? Negative 2.
I'm sure I do this. So the e negative x to the square.
So it's e to the negative 2x. If you have a power to a power, you multiply the 2 exponents.
So that can
Square.
do e to the negative 2x.
That's right.
And since it's a power, that's linear, divide by, simply e to the negative 2x. Divide by negative.
Right. Yeah.
Into a constant, just take out the constant.
So is everybody okay with the area of the circle? We take the radius, we're going to multiply it by pi. We're going to do pi r squared. So we're going to take the radius, square it, and multiply it by pi. And remember that when you are dealing with power to power algebra, you just combine the exponents with multiplication. So this is e to the negative 2x. So that is your area function. And that's the function that we can test. Let's check the left endpoint. That radius is 1. So if we get pi 1 squared, we get pi. So if we plug in 0 over here, we should get pi. E to the 0 is 1. We get pi, so it's checking. So when we go to do our integration, the volume is going to be the integral from 0 to natural log of 4 of that. And then we're back into what we were talking about on Tuesday. This exponent right here is linear. You could use the long drawn out substitution method, or because it's linear, we can use our shortcut, which is the reverse chain rule. And the reverse chain rule, like we talked about on Tuesday, all we do is say to ourselves, the integral of an exponential, or the derivative of an exponential, is itself divided by the derivative of the exponent. And if you were doing a derivative, you would multiply by the negative 2 instead of dividing by it. Really. So that'll be the integration. Just divide by the coefficient of the exponent. Works like a charm. Okay, so now we plug in we have negative pi over 2, e raised to the, okay, that's going to be e to the negative 2 natural log of 4. And then we're going to subtract off that entire antiderivative, so that's minus a minus, so that's going to be plus pi over 2, e to the 0. E to the 0 will be 1. And then here we can simplify also, so we have minus pi halves e to the natural log of, what do we do with the coefficient in front of a natural log?
Put it as a power.
Put it as a power. So this exponent is going to, or this coefficient, so that coefficient's going to jump up as an exponent on the 4. 4 to the negative 2 is 1/8. No, 4 to the negative 2. 1/16. 1/16. So 1/16 is going to go inside this log right here. 4 to the negative 2 is 1 over 4 squared, which is 1 over 16. Plus pi halves. And then I heard somebody say at the e in the natural log, these guys are going to collapse. They undo each other. So we end up with minus pi over 32. Minus pi over 32 plus 16 pi over 32. So we end up with 15 pi divided by 32.
Oh, yes, you're right, yes.
Okay, any question on that? So this 1/16 is from this 4 raised to the negative 2. 4 to the negative 2 is a 16. A little bit off, a little bit here, a little bit there. So one of the keys for creating the disk, remember that this region that we're rotating, it has to be tangent to the axis of rotation. That's not the right word. It has to be touching that axis of rotation. If it's not touching it, there's going to be a hole in the middle of some sort. There's going to be a gap. And that's what we're going to see next. So if we take a look at a region that's not touching the axis of rotation, when we do our rotation, that's going to rotate around, and all of our cross sections are going to be washers. If there's this gap in here, right, we've got that gap, it's going to correspond to a hole. So if we take a single vertical element right there at a random x, when it rotates around, it's going to create a washer instead of a disk. Now, a washer is really easy to find the area of because it's really just an outer disk and an inner disk. Find the outer area, find the inner area, take the difference. And we get the area of the washer. So that's what we're going to do. So now all of our cross sections are washers. We find the area of the washer, we integrate the area of the washer, and we get the volume of the solid. So same basic principle. Same basic principle. So we look at this region here. That region, it's going to rotate around the x-axis, and I've just highlighted here, I took one element and rotated around, and we can see one slice. So the cross section is the washer, but then when we put the dx in there, we add a little thickness, and we get a slice, which is three-dimensional. So we're going to have a bunch of slices added up to create the solid object that we would get. So let's see if we can do it. So there is our representative slice. We're going to take that. Ooh, don't want an arrow on it. Oh, come on, board, be good. So there's our element, our vertical element or rectangle, however you want to envision it. When it rotates around, we get that washer slash cross-sectional slice. So the area of a washer is pi times the outer radius squared minus pi times the inner radius squared. And when we're looking over here at our picture, this distance right here, that is going to be the outer radius. And this distance, let's see, I'm going to write it. I'll try to squeeze it in right there. That's going to be the inner radius. So outer radius is generated from the curve furthest from the axis of rotation, and the inner radius is generated from the curve that's closest to the axis of rotation. So our cross-sectional area, the area of the washer, the area of the annulus, the math word for a washer is annulus, we get pi outer radius squared. So 4th root of x squared minus pi times the inner radius squared. Ooh, that's easy. X squared, yeah. So there is the area of the washer at X. So let's go ahead and simplify that messy looking thing. So this will be pi multiplied, I'll factor out the pi. So when we think about that fourth root of X, it's probably easier to think of it as X raised to the 1/4 power. And then we have X to the 1/4 to the 2. Power to power, you multiply. 2 times a fourth is a half. So this is going to turn into X to the half minus X to the 2. What will be the area of the washer at the left end point? 0, because it just squeezes down to a point, so we have no area when that rotates. So if we plug in 0 here, we should get 0, and we do. What should be the area of the washer at that end point? 0. And that end point, we didn't actually find it yet, but what do you think that end point, what do you think that X value is right there? 1. If we set these two curves equal to each other, let's just do that just to make sure it's clear on how you do that. So if we have the fourth root of X, and we set that equal to X, if this is y equals X. So we would raise both sides to the 4th power to get that. And then that's a classic nonlinear equation. So we put everything to one side and factor. So we'll have x to the 4th minus x equals 0. Factor out the x. Solve for x, and we get x equals 0 or 1. So this, make sure that that process is down. Okay, so that endpoint over here is 1. And do we get 0? If we plug in x equals 1 here, yeah, we get 0. So that area function seems to be the right area function. We are getting what we want to get. And then to get our volume, volume is the integral of area. And the limits of integration, again, are 0 to 1. And so we'll just integrate this function. And that'll give us our volume. Add 1 to the exponent, so we get 3 halves, divide by 3 halves. Plug in a 1, you get 2/3 minus 1/3, which is 1/3. Plug in 0, you get nothing, so we get pi over 3. That's the volume. So a lot of geometry in this chapter. This chapter is going to have a ton of geometry. So it's going to be really helpful to draw little sketches and make sure you're seeing where the radius, where the radii are and things like that. All right, you all try this one. So we've got this region in quadrant 1, this parallelogram looking thing. And we're going to rotate it around the x-axis, and it's going to create this solid object here. Find the volume. Find the volume. If you're having any trouble finding your areas. Okay. That looks like such a nice answer. That is too simple. So the outer radius is x plus 2, so we should have x plus 2 quantity squared. Yeah, exactly, so that minus x can't be in there. So we want so that whole green segment, that whole distance is x plus 2, so we don't want that minus x, yeah. And then that's right, yeah. So then just one little nudge
Same,
with that pi.
that means like,
I like that answer was just a little too clean.
cause you got x squared.
Yep. So that's x squared plus 4x minus 1. Yeah, that's it. Okay. You're on the right track there.
Pi times 4x plus 4 and then you get that, right?
9 times 4x plus 4, but you can multiply by 4 as well.
You get that
plus
plus
1.
48 pi?
Oh,
So it is a good clean answer.
Thank you. So then it'd be.
I don't know if you do.
Some of you did it right.
Area is equal to
Okay, we'll find
4
out.
pi,
We'll find
and
out.
then integrate from 0 to 4, right?
The algebra's looking solid. Yeah. So the area of the washer, pi, outer radius squared, pi, inner radius squared, you can factor out the pi and you have this. So the outer radius is this entire green segment there rotated around, right? That's the green disk is going to be, or the outer disk is going to be that whole radius rotated around. So that's going to be x plus 2 quantity squared minus the inner radius is x, so minus x squared. So that'll be the area of our washer, of a general washer. We square this out, we get x squared plus 4x plus 4. The x squareds cancel. So the volume will be the integral of pi times just 4x plus 4. And we're told that we're going to go between x equals 0 and x equals 4. So those are our limits. Power rule to integrate. So pi, that's going to be x squared over 2. So we get 2x squared plus 4x, 0 to 4. 0 is not a contributor, so we end up with 32 plus 16, which is 48. Very good. 48 pi. Any piece of that you want to discuss? So a lot of Calc 2 and Calc 3 boils down to really pretty basic geometry, finding the area of a washer, finding the area of a disc, finding the area of a cylinder we're going to do next. So let's turn our head sideways. Just like we were doing earlier, you can integrate with respect to x or with respect to y. So everything is just turned sideways. So instead of integrating with a vertical integration element, you're integrating with a horizontal integration element.
And the right minus left still applies.
And the right minus left is going to apply. So when we are looking at so for example, with this one that they show us here, when we are finding the area of that washer, we're going to do the outer, which is going to be the rightmost radius squared, minus the inner radius squared. So we'll do the right minus left thing. So outer minus inner is, of course, that has to happen to find the area of the washer. This curve will be further to the right than that curve. Okay, so That's the basic idea, and we have to have y limits of integration. Let's try one. So here we have the natural log function capped up with y equals 2, and then we're going to stop at the x-axis. So we're going to take that region right there, rotate it around the y-axis, and we're going to create this crazy looking solid down there. There's our generating shape. There's one sample. In this case, it's a disk. Right? There's no gap. We're rotating around the y-axis, and our region is snug up against the y-axis, so there's not going to be a hole. So it's just a disk. So if we take a representative element here at a random y, when that rotates around, it creates a disk, not a washer. Okay, so let's go ahead and find the area of our disk. The area of a disk is pi r squared, so that's our generic formula for the area of a disk. Now the radius is this distance here. Radius is horizontal. Anytime we have a horizontal distance, we need to isolate x. Isolating x is going to be measuring horizontal. So we want to take this function right here and we want to isolate x, so that's going to be x equals e to the y. That is going to be our radius. So the radius is going to be e to the y. So we come in here, we're going to have pi times e to the y quantity squared. And once again, a power to power, you just multiply the exponents. So we're going to have pi e to the 2y. Power to power, multiply. So that is going to be the area of the disk. Now let's just check. Let's check at least the lower disk because that's one that we can calculate. So down here at the bottom, right here, the radius is 1. So the area of that disk at the bottom should be pi 1 squared, which is pi. Now that's a y value of 0 down there. So we plug in that y value of 0 right here, we should get pi. And we do. So that matches. Okay, so there is our area function. The volume will then be the integral of this area function. So we'll pull the pi out, and it's going to be a dy. And so now we look at our y limits of integration. We're going to start down at 0, and we have disks that are stacked up from 0 up to 2. So our y values will go 0 to 2.
We had to switch it, yeah, because it gave us an X. It gave us an X.
All right, so we have to, anytime we're measuring horizontal, we need our functions with x isolated. Anytime you have a function, there's two ways to look at it. You could solve for x or solve for y. If you solve for y, you're measuring this way. If you solve for x, you're measuring this way. So if we want a horizontal distance, we need to have all of our functions written as x values, which means isolate the x. So then you're measuring horizontally. So this is back to our reverse chain rule. As long as that exponent is linear, you could use substitution if you wanted and write a bunch of extra steps. But if it's a linear substitution, RCR, reverse chain rule will always work when that's a linear substitution. And instead of chain rule, where you multiply by the derivative of the exponent, we divide by the derivative of the exponent. So that's reverse chain rule.
Yeah.
All right, and then we just have to evaluate our antiderivative on the endpoints. So plug in a 2. I'm going to write this as pi over 2 multiplied by the quantity. So I'm just going to think about keeping the pi over 2 out in front. Plug in the upper limit of integration, we get e to the 4 minus, plug in 0, e to the 0, 1. So there is our volume. Any issues? Questions? Comments? Bright ideas? Let's see, okay. So here's another one. This one's gonna create a washer, but we're rotating around the y-axis, we're clearly gonna have to integrate with respect to y. So, when we imagine our horizontal integration element right there at a random y, we are measuring horizontal distances. So our inner and outer radius, this is going to be our inner radius right there. The outer radius is going to go all the way over to there. Those are horizontal. So the functions have to have x isolated. They have to be written as x values. So what we're going to do is say, okay, this curve right here, we're going to write it as x equals y. That one's pretty easy. And this other one, we're going to write as x equals, yeah, y divided by 2, exactly. So that will be the left one. So I think we should be able to write down the area of our washer. So the area of our washer is pi times outer radius squared minus inner radius squared. So this will be pi multiplied by, outer radius is all the way over to there, so that's y squared. Inner radius is that one, so square that one, we get y squared over 4. It's really easy to get your letters mixed up. One thing that I would recommend is that if you draw your element, if it's horizontal, you should be thinking the integral will be with respect to y. Everything has to be a y in there. Can't have x's with a dy. Everything has to be the same letter. So our volume will be the integral. They give us the integration limits 0 and 6. We can put the pi out in front. Oh, y squared minus y squared over 4. That's easy, right? That's 3y squared over 4. And then we just integrate that. So we're going to have pi out in front. That's going to be y cubed over 3. The over 3's cancel, so we get y cubed over 4 from 0 to 6. 0 doesn't do anything. 6 cubed divided by 4, so we have 3 6's up there. So that's going to be 6, 6, 6, but we can cancel out 2 2s, so it's going to be 6, 3, 3, so it's 9 times 6, which is 54. Ooh. Something like that. Trust me on that.
Do 6 squared.
6, 6, 6.
By 4 is 9 times the last 6 is 9 times 6.
Yeah,
There we go. There we go. 6, 6, 6, and a 2 and a 2. 2 2's cancel. We have 2 3's and a 6. All right, there. We'll stop. We'll stop doing math for now. I'll stick around for 45 minutes if anyone wants to do math or have questions, have something you want to work on. I will be here for 45 minutes. Yeah.
Right here.
Yeah. Let me just pause that thing.